in this, our fifth lab, we're going to be making column plots and also histograms. So to make our column plots, we're going to use a new geome call, and we're going to use it in a couple of different ways. Initially, we're going to use it to make a column plot when we've got a single predictor variable, and then we'll make a column plot when we've got two predictor variables. We'll continue on to think about how we could put error bars on those column plots, talk about some additional topics, and then finally think about another geome, a geome that we could use to make a histogram. So we're focusing first on this new geome call that's used to make a column plot. And the thing about column plots is typically they're more used for presenting data than they are for understanding data. And in the context of this, we're going to look at position equals. So what do I mean by that? Recall that every geome has these 5 different things. It's got the data, it's got the aesthetic mapping, it's got the options that we represent as 3 dots, it's got the stat, and it's got position. And up until now, we've not considered either position or stat. In this particular lab, we're going to have to think about position. So we've got as goals, we want to produce this plot where we've got a single predictor. In other words, we're interested in demonstrating what the average city mileage is with a single predictor drive. And then we also want to look at column plots, as in plot 2, where we've got 2 predictors. So we're still interested in average city mileage, but now we've got 2 predictors, drive, and the year in which the vehicle was manufactured. So, geome call, just an overview slide, and we're presenting it in the form of that template that we've seen so many times before. We're going to have to modify our data frame. We're going to have to modify our data frame because now we don't want to look at all the data. We just want to look at summarized data. So we'll inherit that data as before. We'll put drive, for example, on the x-axis and average city mileage on the y-axis. The options and the stats we may need to address, but for the first time, we're explicitly going to have to deal with this factor of position. So this is our goal. We want to make this particular plot, and it really summarizes the data by showing the average city mileage as it relates to those different drives. So if we think about it, we've only got 1, 2, 3 values here associated with the 3 values of city average associated with these 3 drives. So we need a summary data frame like this if we're going to make this summary plot. So how do we make this summary data frame? Well, what we're going to do is to create this new data frame, MPGA, we're going to start off with MPG. There's our piping operator, and then we're going to group by drive. We're going to use a summarized statistic to create this new variable, city average, which was the mean of city mileage in the older data frame, MPG. So as always, anytime you use summarize with group by, you can think, how many records am I going to have? The number of records is going to be equal to the number of levels in the grouping function. So drive has 3 levels, 4, F, and R, so there's only going to be these 3 records. How many variables are going to be present? Well, the only variables that are going to be present are those that are either specified in the grouping statement or created by the summarized statement. So we're going to have these 2 variables, drive and city average. So those are the 2 variables that we've got. Once we've got this data frame that consists of 3 records and 2 variables, we can make the plot with this code here. So there's our plotting function. We specify the data frame that we just created, and then the syntax is pretty simple. There's our new geome with its open and closed parenthesis. Inside that, our aesthetic mapping with its open and closed parenthesis. We put drive on the x-axis and average city mileage on the y-axis. So what I want to do here is I want to change the orientation of the axis text x. So before it was 4, and I want to flip it, F, flip it, R, flip it. So recall, this is the way we made the data frame before. In order to accomplish the goal, in order to flip this axis text, what we're going to do when we make our plot is we're going to use the same data frame, and we're going to make the plot initially in the same way, but not surprisingly, if you remember about the lab preparing plots for publication, what we're then going to do is we're going to add to it. We're going to add to it a layer, and we're going to use the theme function. So So there's a theme function with its open and closed parenthesis. And always, how do we do this? First, we name the element. What's the name of this element here? The name is axis text x. It's text. So we hit it with the element text function. And there's its beginning and its closed parenthesis. And inside that, we put the code that'll make things right. So we set angle equals to 90. And what I've discovered through trial and error is if the VJust, that stands for vertical justification, is 0, and HJust, that stands for horizontal justification, is 1, then things work out pretty well. Now what I'm going to do is something else. If we look at the way those drives appear on the x-axis, they appear in alphabetical order with numbers preceding letters. So what happens if I want to change the order? What happens instead of wanting to have 4FR, I want the order to change, so it's now RF4. How do we do that? So this is just a recipe. It's not worth trying to understand it. I think you just accept the fact that it works. So what we're going to do is we're going to create a new variable called drive1. And it's going to be based on the previous variable drive, but it's going to have the values of the drive in this desired order. So if we're going to create a new variable, what function are we going to use? Well, not surprisingly, we're going to use the mutate function. So there's our mutate function with its open and its closed parenthesis out here. Now recall how the mutate function works. We begin by specifying the name of the new variable we want to create. So I want to create a new variable called drive1 as some function of some other variables. And so the function we're going to use, and again, this is a recipe, you're going to use the factor function. So that's in Courier font. You type it in exactly like that, and there's the open and there's the closed parenthesis of the factor function. Then you put the name of the old variable. So this new variable drive1, with the drives in the desired order, is going to be based on the old variable drive. So you state the old variable, a comma, and this is in Courier font. You do it exactly like this, a recipe that's not worth trying to understand. You have levels equal, and then you put in this vector. So here's the vector of values that you want to put in. And the things here, R, F, and 4, are exactly, in a sense, the same levels as in drive. What's changed is the order. What's changed is the order. So the key thing is you're going to put these things in, and they're going to require quotes, because these variables are characters. You're going to put those things in, but you're going to put them in the desired order. So here's the code that actually does that. So we want to create this new data frame that's going to begin with MPG. And we want a summary data frame. So as in the earlier code, we're going to group by drive and use a summarized statistic to calculate average city mileage. So at the end of this step, when we're at this point here, what will we have? We'll have a data frame with 3 different records corresponding to the 3 different drives and 2 variables, drive and city average. Then I'm going to continue on. And how do I continue on? I continue on with my piping operator. And then I use mutate to create this new variable drive1 that uses the factor function. It's based on drive. It's got the same levels, but now they're in the desired order. Now, you don't have to do this, but if you were to type in structure of MPG, if you were to ask for the structure of this thing, this is what you'd see. And so you'd see you've got 3 different variables now. You've got drive, you've got the average city mileage, but now you've got this new variable that you've created, drive1. And the thing that's noteworthy is if you look at drive, look at the order. 4 first, followed by F, followed by R, whereas when you look at drive1, those different drives are in the desired order. So to make the desired plot with the drives in the desired order, then we specify this data frame, and now what we do is put drive1 on the x-axis. So we put drive1 on the x-axis, and drive1 has the drives in desired order, put city average on the y-axis, and we get exactly what we want. So now I want to think not only about changing the orders of the bars, but also change how they're colored. So these are the results of the last federal election. I think things are going to be a little different come October. And what I want to do is make a plot like this. And there's two particular features of this plot. First of all, I want the standing. So we've got the different political parties and the number of seats they won in the last election. I want the parties left to right with decreasing number of seats. And the next thing I want to do is I want to have these bars have the colors or fills that are associated with a particular party. So you get dark red for the Liberals and dark blue for the Conservatives and orange for the Dippers, etc. So how am I going to do that? Well, the first thing I need to do is if I want these parties ordered properly from left to right, then I'm going to begin by doing the trick that we saw in the last slide. So I'm going to create a new data frame called election 1 that's based on this old data frame election. And what I want to do is I want to manually change the order of the parties. So I'm going to use the mutate function to create this new variable party 1, use the factor function. The new variable party 1 is going to be based on party, levels equals C. I type the names in here, inside quotes as the characters, exactly as they are shown here, except now I put them in the desired order. So once I've got this new data frame election 1 in hand, I can use election 1 to make the plot. So how do I make this plot? What I put on the x-axis is party 1. So party 1, as you recall, is just like party, except now I've got the desired order. So by putting party 1 on the x-axis, I get the desired order on the x-axis. And I put the number of seats on the y-axis. And then what I do is I fill by party. Now what's this fill by party all about? Well, if we think about these columns act like those shapes when we went over genome point. They're like those little squares where fill equals determines the predominant color and color equals controls only the border. So what I want to do is I want to map fill onto party. So each one of these records is red and each one of these columns gets a different fill. Now, the problem would be that by default, R is going to use its color wheel, and it's going to pick its favorite 5 colors for these favorite 5 parties. But the whole idea, and one of the beauties of ggplot2, is that if you're making a PowerPoint presentation or a PowerPoint presentation or a poster, you might want to do something kind of cute, like putting in appropriate colors. So how do you do that? Well, the way you're going to do that is, as we've seen before, remember we did this. We had our initial plot 0, that looked like this. And to make plot 3, we started off with plot 0, and we added scale, color, manual, values equal C. We paid attention to our order. The premium got red, and the regular got black. So that's what we're going to do here. Except now, instead of scale, fill, color, what we're going to use is scale, fill, manual. And so it's fill because fill is the key word that describes the predominant color. So this is the scale we're going to use. Scale, fill, manual, values equal C. And again, the order matters. The order is dictated by the order we created when we made this new data frame election 1. So then I just go on to either this particular location or some other location and find the whole suite of colors that are available for ggplot2. And these are the ones that seem to match up best. Red, medium blue, orange, sky blue 2, and green 3. In the last series of slides, what we were looking at was how to make a column plot when we had a single predictor variable, drive. And we were looking at the effect of drive on mileage. Now I want to shift topics and think about a situation where perhaps we've got 2 different predictors. Now, anytime you've got 2 different predictors, one of the things you got to think about is whether or not those 2 predictors are crossed or whether they're nested. And in this particular lab, we'll think about crossed factors. In the next lab, we'll think about nested factors. So what's this distinction between crossed and nested? Well, on this side, we have crossed, and on this side, we've got nested. So here's an example of an experiment with crossed factors. So we've got two factors, fertilizer, water. So we can imagine doing an experiment on plant growth. We get ourselves a bunch of pots, and some of the pots get nitrogen, and some get phosphorus, and some get non-fertilizer. And of those pots, some get water, additional water, and some are left unwatered. So pots that get nitrogen get either this or this. Pots that get phosphorus can get either this or this. Or if you want to flip it around, pots that are watered, some of them get nitrogen, some of them get phosphorus, some of them get none. So in other words, you've got every possible combination. So this is crossed. Nested. In nesting, for example, we've got model nested inside of manufacturer. For each value of model, there is one and only one manufacturer. So Expedition is associated only with Ford, Explorer only with Ford, Civic only with Honda, etc. Another example of nesting is cities are nested inside of provinces. Cities are nested inside of provinces. So Victoria is associated only with BC. There's no Victoria, Alberta. There's no Victoria, New Brunswick. There's an Edmonton, Alberta, but no Edmonton, BC. So as I said, in this lab, we're going to consider how to make a column plot when we've got crossed variables. Next lab, we'll think about nested variables. So previously, we did this. And now what I want to do is add a factor. So now we're interested in the effect on city average, not only of drive, but also of a new factor, a new variable, year. So now we've got these two predictors, drive and year. So we're going to have this summary plot that's going to have these 6 different values corresponding to 3 drives, 2 years. So in order to make that plot, we're going to need a summary data frame that has 6 records corresponding to the 3 different drives, the 2 different years, and average city mileage. So how do we do that? This is pretty much reviewed by now. We group. We group by drive and year, and that's going to give us 6 records because we've got 3 drives and 2 years. And how many variables are we going to have? What variables are going to have? We're going to have drive, year, and city average, drive, year, and city average. So we've got that data frame in hand. We've got that summary data frame in hand, and now we're going to make the column plot. So we use our geom call, added with a plus sign, and there's its open and its closed parenthesis. And inside of that, we're going to do our mapping with its open and its closed parenthesis. And we're going to put drive on the x-axis. We're going to put average city mileage on the y-axis, and then we're going to map fill onto year. As I said before, in the last slide, fill is one of these guys. So fill determines the internal color. Color keyword determines only the border. And so we get a plot like this, which has 2 very obvious problems. And the first obvious problem is that year is treated as a continuous variable. So what we've done is we've mapped fill onto year. So what's going on here? Well, earlier on we saw a slide that looked like this. And the point was we're going to do an aesthetic mapping. So there's its open and closed parenthesis. And we're going to map color. And we can map color onto a discrete variable such as drive and get 3 discrete colors. Or we could map color onto a continuous variable displacement and get a continuum, a gradient of colors. So what's happening here? What's happening here is that year is one of these guys. It's an INT. It's an integer. R thinks that year is a continuous variable. Now, we think it's a discrete variable because we've only got two levels. But it doesn't matter what we think. What matters is what R thinks. And R thinks it's a continuous variable. So what it's doing is it's giving us two shades of blue, a really light blue and a really dark blue. Now, because we've only got two levels, this doesn't look too bad. But look at the legend. The legend here clearly shows that it's not viewing year as a discrete variable. So that's the first problem. And the second very obvious problem is that these bars are stacked and we want them side by side. So how are we going to deal with the first problem? The problem that R views year as being a continuous variable. How do we make it into a discrete variable? Well, this again is just a recipe. So don't bother trying to understand, just understand that it works. So in order to make our summary data frame, we're going to start off with MPG. We're going to begin as before by grouping by drive and year and creating the summary statistic city average. So that'll give us the 6 records and the 3 different variables. But now what we're going to do is I'm going to create a new version of year. And it's going to be based on the old version of year. But by using the as factor function, I'm going to change it from being a continuous variable into being a discrete variable. Now if I use this new data frame MPGB, and I put drive on the x-axis and city average on the y-axis and fill onto year, now I've got these two discrete colors, the two colors that we typically see when we map a discrete variable onto a factor that's only got 2 levels. We see the orange and the salmon, but now, perhaps more importantly, we have the legend that makes sense. We still have, however, the problem that these bars are stacked on top of each other, and we want them side by side. Well, just as an overview slide, let's remember this template. And just remember the fact that we start off with our plotting function, we add as a layer a geom, and every geom has these things, 5 things, the data, the aesthetic mapping, the options, the stats. Everything up until now is okay. We've not had to look at position before. Now we're going to have to address position, and we're going to do that with saying position equals dodge. Everything here is in courier. Dodge is in courier, and you're going to need the quotation marks. So this is the plot that we just looked at that used it data frame MPG. It had MPGB that had year as a factor. Drive went on the x-axis, city average on the y-axis, and fill according to year, but these things are stacked. To get what we want, what we need to do is we start off with the same data frame, the aesthetic mapping is the same, but now outside of the aesthetic mapping, so this is the open and the closed parenthesis of the aesthetic mapping, outside of that, for the first time, we're going to have to use a position statement, and we're going to set the position equal to dodge. And so we get something that looks like this. If you want to remember this, it's quite simple. If you think about the game dodgeball, how is that played? Someone throws a ball at you and you jump to the side. So what dodge is essentially doing is it's jumping these columns side by side. So we try to put this all together. How are we going to make this plot that has 2 different predictor variables for this dependent variable city average? So we're going to start off with making the new data frame. And so there's 2 components to that. First of all, we're going to have to convert year from being continuous to discrete by using the factor function. And then we're also going to have to make a summary data frame. So we've got just the 6 different records with 3 different variables. And once we've got this data frame in hand, this is the code that does it. Drive goes on the x-axis, average city mileage on the y-axis. We want different bar fills depending on the year, so we map fill onto year. So that's the beginning and ending parentheses for our aesthetic mapping, followed by a comma. Now we're going to have to change the position by stating the keyword position and stating dodge. So one of the nice things about ggplot2 is that if we're making these column plots, it's really easy to switch what's on the x-axis to what's in the legend. So here we've got drive on the x-axis and filling by year, so year is in the legend. Very easy to change that. You just put drive as the fill and year is the x mapping, and now we've got drive on the legend and we've got year on the x-axis. So all the things that we just went over will work really well if you're going to do a PowerPoint presentation or a poster. But if you're doing a black and white publication, then you may want something like this. So I'm going to assume that there exists this data frame called DF-Fill that's got these 5 different manufacturers, 2 different years in which they were made, and average city mileage. So I've got this data frame, DF-Fill, and I want to make this particular plot would be suitable for a black and white publication. So how am I going to do that? Well, I'm going to put year on the x-axis, map x on the year, city average on the y-axis, map y on the city average. I want different colors for these different bars, so I map fill onto manufacturers, because again, remember we got a rectangle and fill determines the internal color. So that is the beginning and the ending of my aesthetic mapping. I'm going to need a position statement. So one of the things you may wonder is, how do I determine when I need a position statement and when I don't? And the really simple way to think about it, that is, ask yourself this question. For any one value on the x-axis, do I have one or do I have more than one value on the y-axis? So in this particular case, for 1999, for that 1 year, I've got 5 different values. Similarly, for 2008, I got 5 different values because I've got multiple values associated with both of these years. I'm going to have position equals Dodge there to override the default so that these 5 columns aren't stacked on top of each other. So I'm going to need position equals Dodge. And then I'm going to add scale fill manual. So we saw scale fill manual earlier, but now I'm going to pick some values that are suitable for a black and white publication. So there's the open and close parenthesis. There's my values, and here's my vector. White, gray 75, gray 50. Again, the order matters. So white is going to be the Audi, and gray 75 is going to be the Dodge. And I must admit this is a bit counterintuitive because gray 75 is actually pale gray, and gray 25 is actually dark gray. So what's this color equals black business? What's that all about? And notice there's the open and close parenthesis of my aesthetic mapping. So this specification of color equals black is a setting. What's going on? What's going on, again, is that with these column plots, they act just like the rectangles in a scatter plot, where fill is the predominant color and color is just the border. So I've mapped fill on a manufacturer, so I get different internal colors for the different manufacturers. But what I'm doing is I'm setting color equal to black. By setting color equal to black, I'm putting a black border on each of these. Well, why would I want to put a black border on each of those? The reason I want to put a black border on each of those is that look at this first column. It's white. And so I need to put a black border on it so I can see the sucker. There's an alternative way that I could have prepared this plot for a black and white publication, and we got some hint of that in an earlier slide. This one. So remember we had our plot 0. We said, okay, for a black and white publication, we might want something like plot 2. And the way we made plot 2 was to start off with plot 0 and add scale color gray. That's what we're going to do here. So we're going to have this data frame, DF fill. We're going to specify that. Year goes on the x-axis. City average goes on the y-axis. We fill onto manufacturer. We've got multiple observations for the different years, so we're going to have the position statement, position equals Dodge. But now what we're going to do is we're going to add scale fill gray. And what I've shown here is I've specified starting and ending points, and by specifying a 0 and a 1, the fills are going to go between complete white and complete black. As before, however, if I think about my aesthetic mapping, and it's open and it's closed parenthesis there, outside of that, as an option, I'm going to set the color equals black. Setting the color equals black is going to put a black border on all these columns so that I can see this one here, that is white. So previously we produced plots that look like this and plots that look like this. And now we want to look at a new geome error bar, that we can use to add error bars and produce plots that look like this or this, where this distance here is 1 standard deviation, and this distance here would be 1 standard deviation of the city mileage for front and rear wheel drive vehicles respectively. So in order to produce a plot that looks like this, that has 3 different drives, and then it's got the average city mileage for each of those drives, and then have these error bars that extend 1 standard deviation in each direction, we're going to need a new summary data frame that has 1 record for each one of the 3 different drives and 2 summary statistics, the average city mileage and the standard deviation of city mileage. Producing that data frame is fairly straightforward. We start off with MPG. There's our piping operator, and then we group by drive. If we group by drive, we're going to have 3 records in our final data frame corresponding to the 3 different drives. How many variables are we going to have? We're going to have 3. We're going to have drive. We're going to have the average of city mileage, and this is the code here that will calculate the standard deviation of city mileage. So once we've got this data frame in hand, we can then make this plot. And we're going to rely on the fact that ggplot2 is a layered language. So we're going to have our plotting function as a layer. We're going to add to that geome call to produce the columns. And then we're going to add to it this new geome error bar that's going to put in these error bars. So that's our approach. So we reference our data frame, and this is the code that we've seen before that would produce these columns. And now what we need to do is add these error bars. So we're going to add those with geome error bar attached as a new layer. And we really got a couple of challenges. What we need to do is we need to be sure that we've got these error bars, this one for example, lined up on top of the appropriate column. And the second thing we're going to have to do is we're going to have to specify a couple of values. This value here, which is ymin, the bottom of our error bar, and this value here, which is ymax, which is the top of our error bar. So how's that going to work? So there's our geome error bar, and there's its open and its closed parenthesis, and we've got an aesthetic mapping with its open and its closed parenthesis. So what sort of aesthetic mappings are we going to do? We're going to map X onto drive, and that's going to get these error bars lined up on top of the appropriate columns. And then we're going to have to specify this value here, ymin and ymax, and here's the code that's going to do that. Now, as you can see is happening here is we're actually doing some algebra inside of our aesthetic mapping. So we're taking the value of city average and we're subtracting the standard deviation from it. We're taking the value of city average and subtracting the standard deviation from it. There is actually another way to do business, and we'll see that in the next slide. I could have produced a data frame that had this calculation and this calculation built into my data frame, and then I could directly have added those values of ymin and ymax to my plot. Either way works fine. We'll see the other way in the next slide. So what we've done now is, up to this point, we've got our aesthetic mapping. Then outside of the aesthetic mapping, as a setting, there's some settings we're going to do. We specify color equals gray, and that's being applied to the error bars. So these error bars have a gray color that will enable them to stand out both against the white background and against the black column. Size equals controls the thickness of this line. And width, what is width control? Width controls the distance of this little top part, this little hat that sits on the error bar. So now we're going to do something a little bit more complicated. We're going to make a plot that has 3 different drives, 2 different years, and we want to add error bars to that plot. So as before, we'll need a summary data frame. We'll need the 6 different combinations, because we've got these 6 different points here corresponding to 3 drives and 2 years. And then we'll need a series of summary statistics, the average city mileage and the standard deviation of city mileage. And as I mentioned previously, this time I'm going to do business slightly different. I'm going to calculate average city mileage plus standard deviation, average city mileage minus standard deviation directly in my data frame, and then I'm going to use those to determine my Y min value down here and my Y max value up there. So here's the code that's going to make that data frame. So I'm going to start off with MPG, and then what I'm going to do is this, and this is just a recipe we've seen before. I'm not sure that it's absolutely essential, but hey, why take a chance? Year. Year to me, I'm going to view as being a discrete variable. In the mind of R, it's a continuous variable. So what this code here does is it shifts year from being a continuous variable into being a discrete variable. And then I continue on and I group by drive and year. By virtue of grouping by drive and year, that's going to give me these 6 records corresponding to 3 different drives and 2 different years. And then I'm going to create 2 summary statistics. City average, which is the average city mileage, and city SD, which is the standard deviation of city mileage. So think about where I would be at this point. If I stopped right here, what would I have? What I would have at that point would be this data frame right here. I'd have those 6 combinations of 3 years and 2 drives and these summary statistics. But now I'm not going to stop there. I'm going to continue on. I'm going to continue on to use the mutate function to create 2 new variables, Y min city and Y max city. And Y min city is just city average minus the standard deviation, and Y max city is just city average plus the standard deviation. So we can see here that if we took 14.2 and subtracted 2.6, we get 11.6, or if we took 14.2 and added 2.6, we would get 16.8. So now we have our data frame in hand. Now we have our data frame in hand, and we can make this plot. And as before, we're going to have those 3 layers. We're going to start off with our plotting function. Then we're going to add some code to make the column plot. And then we're going to add some more code to superimpose those error bars. So the first bit is pretty routine. There's our plotting function right there, and it specifies a data frame. Then we add as a layer the code to make the column plot. And this is code that should be fairly familiar by now. Year goes on the x-axis, city average goes on the y-axis. We map fill onto drive. As a consequence of doing that, we'll have these different colors for the 3 different drives. Position equals dodge. Remember the way this works. Do you need to dodge? Do you need not to dodge? The question can be answered by asking yourself, okay, for each one of these years, do you have 1 or do you have more than 1 y value? Well, clearly you have 3 y values for each given year. As a consequence, by default, those columns would have been stacked on each other. You need position equals dodge in order to jump them side by side. So those are the first 2 layers. And then we're going to add as a 3rd layer with a plus sign, geom error bar. And there's the open and close parenthesis of geom error bar. And there's the open and the close parenthesis of our aesthetic mapping. So again, we have the same challenges as we saw before. We got to do a couple things. We got to need to have these error bars lined up on top of the appropriate columns, and we need to specify Y min and Y max. So here's the code that's going to do that. We're going to map the X location onto year, and we're going to map fill onto drive. And if you stop and think about this last bit here, that ought to strike you as being quite strange. Where have we used fill before? Well, we've used it either for geom point, when we had markers that look like that, or we also used it, obviously, up here with column plots when we had rectangles. And the whole idea was that when we used fill, anytime we use fill, that fill equals determine the predominant color inside, and color equals determine the shade on the border. So this ought to seem strange because geom error bar, that's making these thin little lines, these little error bars here. How can we possibly fill a line? What's going on here? I'm pretty sure that what's going on here is we're trying to locate these error bars so they sit on top of the appropriate columns. And so the way we located these columns vis-a-vis the x-axis was x equals year and fill equals drive. So I think the reason why we need x equals year and fill equals dry for our geom error bar, even though it doesn't make any sense to fill a line, is that that's being done to appropriately locate our error bars on top of the right columns. So those are the first aesthetic mappings. Then we continue on and we map ymin onto ymin city and ymax onto ymax city. And then we're done with that. So then we're done with the aesthetic mapping right there, and we follow it with a comma. Now when we think about our column plot with geocol, we had position equals dodge. We're also going to have a position statement in geom error bar. And look at that code. Look at that code. It's all in Courier. Even this 0.9 is in Courier. What's going on? Well, there's some pretty ugly algebra involved. If you're really interested, you can go to Appendix 15 and see what that is, but you'll actually want to type in the 0.9. Then following that, we also have width equals 0.2, and width, as you recall, determines the width of this little guy here, and size equals 2 determines the thickness of our error bar. So, switching topics and thinking about Cleveland dot plots. Here I've got the 38 different models that are in the data frame MPG, and here's the average city mileage associated with each of those, and that's pretty hard to read. A more readable version would be to have the models on the y-axis and average city mileage on the x-axis, and that's known as a Cleveland dot plot. So, in order to make this plot, we're first going to have to make our summary data frame. It's going to be a fairly simple data frame. It's going to have 38 rows corresponding to the 38 different models, and it's only going to have two variables, model and average city mileage. So we group by model, so that's going to give us our 38 records corresponding to the 38 models. Then we're going to create this single summary statistic, which is average city mileage. Once we've got this data frame in hand, we can make our plot. So we got the data frame, and we're going to make a scatter plot. We're going to make a scatter plot, and there's the open and the close parenthesis of the geom point, and then we're going to do a couple mappings. On the x-axis, now it's kind of a switch. We're going to put average city mileage on the x-axis, and here's the really important thing is right here. We're going to map the y location. Y location is mapped like that. And we're using the reorder function. And this reorder function takes two arguments. It takes this argument, and it takes that argument. This argument here, model, what that does is that means that what's going to be on the y-axis is going to be the model. What the role of city average is that because we're using the reorder function here, city average is going to determine the order in which these models appear. And they're going to recur in such a way that when you look at the order of these models, that they reflect an increase in city mileage. So that's the particular plot we made. If you're only interested in visualizing your data, that would be adequate. If you actually wanted to make a plot for publication, you might want to look at Appendix 4. This is just a little problem that you may arise if you're plotting out your data. So what I'm interested in is looking at the different combination of 5 levels of fuel. There's my 5 levels of fuel and 3 levels of drive. 3 levels of drive. Now what you'd expect is that with 5 fuels and 3 drives, multiply those together, you should have 15 records. But if I actually took MPG, grouped by fuel and drive, and then created this summary statistic miles, which is the average of highway mileage, I get a data frame that looks like this that has only 12 records. And the reason it has only 12 records is that some of these combinations of fuel and drive are missing. The reason that becomes a problem is pretty obvious when we look at the plot. We've got these different width bars depending on the drive as a consequence of missing records, and that's pretty ugly and pretty unacceptable for your thesis. So how do you solve that problem? Well, to me, the best way to solve that right now is to modify the data frame. And so if we were expecting 15 combinations, but only had 12, then the thing you do is to locate the 3 missing combinations. I've done that there and assigned them a really small value. And then having done that, when I actually make the plot, using this new modified data frame, I can see appearing down here where those 3 different lost data points were, and now they show up as very thin lines. By default, you're likely to get a plot that looks like this. You might want something else. You might want thinner bars. You might want to play around with the spacing between the bars. If you want to do that, you can consult Appendix 15. And in terms of adding error bars, should you decide to go with these column plots with thinner columns and some space between them, again, Appendix 15 will cover that. Distributions. Now, making a major shift in topics, I want to talk about distribution. And the concept of a distribution, it's the frequency of occurrence of different values of a particular variable. So, here's an example. This shows a frequency distribution, or a histogram, you might call it, of city mileage. So what I've done is I've taken front-wheel drive vehicles only. So I'm only interested in front-wheel drive vehicles at this point. And I've taken that continuous variable, city mileage, and I've had it chopped up into a number of bins. So it's chopped up into a number of bins, and then I'm counting the number of records in each bin. Now, these little numbers here, those were put in PowerPoint, those weren't put in by R, but the basic idea is if we think about this continuous variable city mileage, there's a bunch of records that fall in this range that have a city mileage that goes from 16 to 20. And there's 53 of those guys, and there's 33 guys that have a city mileage that goes between 20 and 24. Here's another distribution we saw a lot in lecture, the normal distribution. These show what would happen if you took a pair of dice and you rolled those dice and then you counted up the number of spots. So if you take 2 dice, you toss them, count the number of spots, you might get a total of 2 dots or 3 dots or 4 dots or 5 dots. And what this particular plot is meant to represent is the number of different ways of getting either a total of 2 dots, a total of 3 dots, a total of 4 dots, etc. So if we think first, how many ways are there to get a total of 2 dots? There's only one way. You get a 1 on the first die and 1 on the second die. If you ask yourself, well, how many ways are there to get a total of 4 spots over 2 die? Well, you either get 1 plus 3, or 3 plus 1, or 2 plus 2. And then how about how many ways are there to get a total of 7 dots? Well, you get a 1 on the first die and the 6 on the second, or 6 on the first and 1 on the second, etc., etc. So that's what this plot is meant to show. So this shows the count of the number of different ways you could get different totals of spots over 2 dice. Now, if you add up the 1 and the 3 and the 6 and all these other values, they add up to a grand total of 36. So what I've done here is I've made this plot, which is essentially taking each one of those counts, the 1 and the 3 and the 6, and then divided them by the total number of counts that I might have gotten, total number of these, and then I get a plot that looks like this. Now, the shape is exactly the same, but a couple things have changed. First is, now what I have on the y-axis is density. And the difference between density and count is that here we've got the actual count. Here you've got what is essentially, I'm going to call it density, but it's essentially taking a count, dividing it by the total, so that the total value of all these things adds up to 1.000. And because the total now adds up to 1.000, we can consider that to be a density plot as opposed to a plot of counts. So, that was an introduction to distributions, and we're going to examine 4 different geomes for looking at distributions. And in the remainder of this lab, we'll look at geome histogram, and then in next lab, we'll think about these 3 other geomes for looking at distributions. When we consider distributions, there's a couple things we need to think about, whether or not those geomes use bins whether or not those geomes summarize the data or, in contrast, show all the data. So the whole plan is, over the next bunch of slides, we're going to look at different geomes and how they can be used to evaluate different values of highway mileage for the 3 different values of drive. And so I'm going to begin with geome histogram, and I'm also going to begin with a confession, because although I just said that the whole idea was to compare the distributions of highway mileage for the 3 different drives, initially I'm only going to look at front-wheel drive vehicles, and the reason for that will become apparent later on. So the whole plan initially is to make something that looks like this, a histogram. It's going to take this continuous variable, highway mileage, it's going to cut it up into bins, and then for each bin, it's going to record on the y-axis, going to illustrate on the y-axis the number of records associated with each one of those bins. So, as often has been the case, we will return to this template that we've seen many times before that says we're going to have our plotting function, and then we're going to add to it a geome, and the geome is going to have those 5 things: the data, the aesthetic mapping, the options, the stat, and position. And so we can think about how those things are going to operate for geome histogram. So I'm going to begin with a slightly modified data frame that only contains the front-wheel drive vehicles, and the reason for that will later on become apparent. But right now we're only thinking about front-wheel drive vehicles, and so that data is going to be inherited, and there's our aesthetic mapping. We're going to map the X location onto highway, and that's different. We've not seen anything like that before, in the sense that in every other plot we've made, not only did we map the X location, but we also mapped the Y location. So why do we not have a mapping of the Y location? Well, next few slides will go over that in a little bit more detail, but just as a kind of a precursor, what we're going to see is that we've got down here a stat. And the default stat is going to work just fine. But the default stat is called bin. And what that default stat bin is going to do is it's going to create a series of bins. And then for each one of those bins, it's going to count or create a couple of variables, count and density. And this is the one that's really important. For each one of those bins, it's going to count up the number of records in each bin, and that's what's going to go on the y-axis. So we do not need to specify y equals, because y equals is going to be calculated for us by this default stat, which is bin. It's going to create those bins, count up the number of observations in each bin, and put that as the y variable. In terms of options, I would recommend putting in bin width and some number. And the whole idea about it, just geome histogram, is that it makes a series of bins. And what appears in the plot may vary depending on how many bins you have and how wide they are. So to make sure that your conclusions are robust, I would suggest, if this is your own data, that you run multiple plots with different bin widths to make sure that your conclusions are robust. The default stat is bin. It's okay. As I say, its role is to create the bins, count up the number of observations in each bin, and put those on the y-axis, so we don't have to map onto the y-axis ourselves, and the default position is okay. So let's think some more about the stat business, this bin business, what's going on. So basically, as always, we've got our plotting function, and we've got some sort of a geome, and then among those 5 things, there is this thing called the stat. So let's think about stat for the different geomes. So for geome point, geome line, and geome call, the default stat is identity, and that works just fine. And for geome histogram, the default is bin, and that also works just fine. Let's think, though, how it works for geome point, geome line, and geome call. We mapped the Y location on the highway. So the whole idea about this stat being identity is that what goes on the y-axis is identical. To highway mileage. So that's the way it works for these geomes, and it works just fine. How does it work for geome histogram when we map X on the highway? How does that stat work? Well, the default stat is bin, and it creates these two variables, count and density. And then once it's got those two variables, count and density, it puts bin on the x-axis, it puts count on the y-axis, and unless you need it, it doesn't deal with density at all. Although for some more sophisticated things that you might do on your own outside this course, you might actually want to use density, but we're not going to get into them in this course. So by default, bin goes on the x-axis and count goes on the y-axis. So here's an example. Let's say we're looking at highway mileage and we use geom histogram. The default stat of bin is going to, by default, try to create 30 bins. And it's going to create for each bin the count of records in each bin. So the first bin, if it looks at highway mileage, is going to go to 12 to 30 to 13.1, and it's going to have one observation. And there it is. There it is. You see where it sits on the x-axis? It sits corresponding to a bin that goes between 12 and 13.1. And how many observations are here? There's just one observation, just a count of one. And similarly, if we go all the way to the bottom of the 30 or so bins that it's created, the last bin is going to go from about 42.9 to 44. So there it is, located somewhere between 42.9 and 44. So that's the x location. And in terms of the count, what's on the y-axis shows up as a 2. And if you follow this thing across, it would indeed be a 2. So with geom histogram, the default code is actually pretty simple. Now, I said at the outset that I only wanted to look at the front-wheel drive vehicles. So I begin with MPG, and then I use this filtration to retain only the front-wheel drive vehicles. Again, as a matter of review, we've got a double equal sign here because this is a logical test. We only want to retain those records that are front-wheel drive. So a logical test, double equal sign. Also the quotation marks because drive is a discrete variable. So once we've got this data frame in hand, the code to make this particular histogram is really simple. We just specify our data frame, we use geom histogram, and all we got to do is tell it what goes on the x-axis. We tell it highway goes on the x-axis. So highway is going to go on the x-axis, and the default stat of bin is going to take that highway and it's going to chop it up in these little bins. It's going to count the number of observations, number of records in each bin, and that's what's going to go on the y-axis. But as I said, if this is your own work, you probably want to play around a bit with this bin width. So here what I've done is I've changed the bin width equals 4. I have a slightly different appearing plot. And my suggestion would be to run your plots with different bin widths to make sure that any conclusions you're withdrawing about, or any conclusions you're drawing about your data are not highly sensitive to the bin width which you used.